Hello. In this lecture, I will talk about other numerical groundwater modeling tools, such as the USGS Mudflow or VFlow or other common software. Because if you will conduct groundwater modeling simulations professionally, you will hardly use a GIS system, but some more specialized software which is capable to represent more complex hydraulic processes, transport processes, which can also model, for example, heat processes or couplings or those kind of problems, and which is also maybe a bit more convenient in the user experience in the sense that it provides some functionality more easily to the user than a GIS system. So when you decide what kind of software to use, there are a couple of questions you can ask yourself, and it would recommend to have or to prepare first a conceptual model to know what the demands are and then selecting a piece of software. If you are in a commercial company or in some other setting professionally, there is probably one code available, one program licensed, which you're supposed to use, because, well, the variation of problems are usually limited. Right. Still, I want to introduce you today to different kinds of software, so that you've heard about it, that you know what is meant by the different terms, what the benefits and drawbacks are, and so that you can make a reasoned decision. Alright, so you can select what code is best for the particular situation you want to simulate. Not all codes, as I said, have left the same amount of physics available. Right. We'll talk a bit about how accuracy matters for the code selections, though of course you can usually consider that the professional softwares have all of a very, very reasonable accuracy, and they do not diverge so much between different software packages. Right. You might want to make yourself sure about what the data requirements are for the code in specific, and then for your problem. Know that the parameterization of the models will slightly might slightly vary across codes, though, you know, VFlow, for example, usually goes by hydraulic connectivity and aquifer thickness. Others will operate on transmissivity directly. So, you know, code vary, but that's something you can, you know, by hand recalculate one value from the other. But still, there is maybe slight variations. Right. You want to know maybe what capabilities you need in terms of hardware. Is there support technically for the software and stuff like that? Right. You might want to know how much training is required. So many of those softwares have a rather steep learning curve. So what kind of documentaries are available and how much do they cost? Right. So set the question for support, because usually if support is offered by professional software, it's usually connected with paying for license, right? So those two are quite well connected. And then, of course, professional software for groundwater modeling can be quite pricey if you use it, especially if you use it in a non-academic environment. So in science, one of the most prominent codes for groundwater modeling which you will find is the USGS Mudflow. So it's developed by the United States Geological Survey. It dates back for quite a long time, which you also notice in some kind of historic developments. So it's written in Fortran, which is very fine software for numerical modeling, though it's often considered a bit outdated. Other languages such as C++ are sometimes more common these days. It is based on finite differences, quite unique this time. So all the more modern software will be based on finite elements. The neat thing here is it is open source. So in principle, you can modify the code, and there are various extensions, modifications, and derivatives of USGS Mudflow, which although sometimes makes it a bit difficult to find the right version for you. Right. So the USGS Mudflow itself is really much focusing on flow modeling, but then there are, as I said, extension things, so you can link it to heat and mass transfer, pre-processing, post-processing, visualization, and all that kind of stuff. As I said, it is very popular in an industrial surrounding as well as in academia. There is a graphical user interface to use it, but it's more common to use it on a script-based variant. So means it has some kind of its own syntax, its own, well, it's not really a script language, but kind of you structure a text file in a very, very specific way and giving commands and values in this script file. And then you can, you run this script within USGS Mudflow and you get a text file as an output, which you then can visualize using some other software. So it is less intuitive maybe as a GIS environment. That's why I designed this course around CrossGIS. But so USGS Mudflow is very powerful. It is sad to have a quite steep learning curve, so it means you have to put a lot of effort in it at the beginning until you understand how it actually works, and then you can go from there on. But it's very powerful, and there are a lot of several specialized packages for specific hydraulic situations. For example, to model seawater intrusion or things like this. So, and as it's open source, you can pretty much go on the website, download the newest version, and play around. All right. So the most prominent versions you might be interested, for example, is Seawatt. This is set for seawater intrusion modeling. It has a variable density flow and transport. That is what you need if you want to model seawater and freshwater interaction. There is a version called PEST++. So PEST is a model, it's a program which allows you parameter estimation. So you can a lot of different simulations with the different parameter settings and see which is the most representative for the situation you're looking at. There is also FlowPy, which allows you to run Mudflow based on Python scripts, which is nowadays quite popular because Python has just become a very popular language to learn in undergraduate studies. Right, and then there is the graphical user interface, which is said you have to download additionally to the Mudflow itself, which is script based. Right, so different ones, I just put Model Muse, which is a graphical user interface for Mudflow, and also some of its derivatives such as Seawatt, which all of those are, as again, open source, free to download. You can just simply download it and apply it. Though again, I mentioned the steep learning curve. All right, so you will find help online. There's a manual, it's well documented, and as you said, it's very, very common, so you will find help on the internet. I'm pretty sure also there are some kind of introductory courses using Mudflow, but there isn't something like a professional company you call to get support for Mudflow, right? It's an open source project provided by the USGS. VFlow is a software package, very common, at least around Europe. It's a commercial software with a graphical user interface. So it is a specialized software for groundwater flow. So it is kind of made for efficiency, and it allows you, for example, extracting or injecting tracer and obtaining variations in tracer concentration or groundwater level at some observation points very conveniently. So it has, on physics way, it has pretty much everything you're looking for. It has groundwater flow, mass transfer, heat transfer, variable density, right, multiple component reaction chemistry. So that it comes with pretty much everything you can wish, and it's not like Mudflow in different packages and stuff. It's just software. You buy it, you download it, you install it, and it's everything there, right? As the name already says, VFlow is finite element subsurface flow system. It is based on finite elements, right? That's quite clear by the name. It covers saturated, unsaturated conditions, so you can also do infiltration modeling with this. It has horizontal simulations, right? For infiltration, you can also have vertical simulations, and you even can do full 3D simulations with it. So there are quite big capability of using VFlow for groundwater simulations. So as it is a commercial software, of course, it comes with a price tag. And as any software, it needs some time to get used to it, though it is often found quite convenient for users. And as it is a commercial software, so there is a big software partner in the background, where I believe you can also buy training courses to get used to it and to learn VFlow to the fullest. There is also a book of similar name, which gives you all the background on the mathematics and the numerics if you want to. Another software very compatible to VFlow in terms of what it covers in the physical properties is Spring by Delta H. So it is same game pretty much as VFlow in terms of that it's provided by a commercial software, professional company, commercial company. So you can buy it, you can download it, you can use it. It's all very convenient. They provide you with online resources to learn how to use the software. There also is a free version to play around with some limited capabilities. But if you just get a glimpse at it, you can just Google it, and then you can download a free version. It includes visualization tools, so it has this post and pre-processing included. It does a very nice job on incorporating realistic geological or hydrogeological settings. So you can include geostatistics. It allows different interpolation algorithms directly from your measuring point, so you don't have to use many other tools. It's trying to get as much things under one hood than trying to rely on external sources. It has a very smart meshing algorithm, so generating the finite element mesh, so it's also based on finite elements. Right, and especially paid attention to having a good incorporation of discrete features, not just structures, but also man-made engineered constructions such as tunnels or mines. And you have very very powerful tool It also comes with learning curves, as there is everything. But again, there are online resources to help you to get started. There's also a book which you can download, I believe. Yes, similar game than VFlow, and it's also actively developed. There's coming up a new version similar to VFlow every couple of years. A slightly different approach or slightly different focus is Hydras. It is. I was struggling including it into this list because it's not strictly speaking a groundwater modeling tool. Because Hydras is very specialized on infiltration models. So it's not solving the horizontal groundwater equation, but it's solving the Richards equation, which is the mathematical equation for infiltration problems, and it allows you to couple that with heat and solid transport. But if you ever deal with partially saturated environments, Hydras will definitely come your way, because it is just so common. And again, there is an open source version which is limiting to 1D, which still is for infiltration to get an idea, very helpful. And then there is a 2D and 3D version, which is commercially distributed by the company, and which is, which you can buy for some license. It's also based on finite elements. And also the great thing that comes with Hydras is its immense database. You don't have to specify parameters, but for example, you can go with the soil type, or you can go even with the ratio of minerals or grain size distribution, stuff like that, and Hydras will automatically estimate you the required parameters, because for unsaturated or partially saturated environments, you require more parameters than just for the full simple groundwater flow. And you can also then select different kind of models which try to approximate the partially saturated environment. So it is really powerful if you deal with partially saturated porous media. And there's also a very nice thing which allows you the estimation of soil parameters if you've got experimental data. So for example, if you come with an infiltration experiment and you know how your moisture content changed over time based on some boundary conditions, Hydras allows the inverse modeling of soil parameters, right? So if you don't know what inverse modeling was, go back to the very first lectures of this series and look up again what inverse modeling was. But this is a very nice feature. But again, Hydras should be connected in your head with partially saturated porous media. If you go towards multi-phase flow, especially in combination with more chemical focus, then you will get probably familiar with TUF. So it's a code for really complex multi-phase scenarios, right? So going a bit away from groundwater flow here, right? So TUF has been developed for reservoir studies in terms of geothermal oil and gas, or waste, nuclear waste deposition. You can have precipitation dissolution of minerals, which then react back to porosity and permeability. You can have reactive flow. Again, also there is an inverse version. So this is really, such as Hydras is specialized on unsaturated flow. If you're talking about chemistry and complex multi-phase scenarios, which go beyond what you can do with Freak, then TUF is a very good tool to take a look at, right? I have never used it myself, so I can't tell you much about the learning curve. But if you have to deal with those kind of chemical couplings, this is a very hot recommendation to take a look at. We come now to a bit of broader software, which is not specifically focused on groundwater flow, such as VFlow or Spring or Mudflow, but which are capable of coming towards more complex scenarios and therefore also could be used to do groundwater flow simulations. OpenGeoSys, for example, is a long-standing open software project, again more actually designed for reservoir problematics. So it has a strong emphasis on coupled problems in terms of thermohydromechanical and chemical processes, right? So similar as it is with TAF, focusing on the chemistry. Here it really has this coupling of thermal processes. So you can model thermal transports combined with hydro flow, so advective diffusive processes pretty much, but now not on the contaminant transport only, but also on thermal processes. And then, for example, the temperature causes thermal stresses, which you can then calculate mechanically, and you can calculate rock failure processes, which then would increase permeability again, or stuff like this. So you know, focusing on those kind of couplings, and well, because coupled processes are demanding to calculate, especially the mechanical part. OpenGeoSys has a strong emphasis on high performance computing, right? So it is capable to run on a single computer as well as on large computer clusters, depending on the problem you want to use it. It has a graphical user interface, but also allows you to script your inputs, which many professionals prefer. And there you see the difference. OpenGeoSys is based on C++, while Mudflow was based on Fortran. So there was some change in development over the years. But OpenGeoSys is something for looking at it on coupled processes. Kind of similar is Dumbox. It is also a free and open source simulator. It's based in C++. It also focuses on coupled and multi-phase problems. So it really is a great tool to model multi-phase flow. In comparison to OpenGeoSys, it has less an emphasis on mechanical processes, but a lot of you know, these multi-phase and heat transfer models are very well elaborated in Dumbox. So there really is also differences in the terms of complexity the different programs use to represent some features. So they really have to dig into the details and look what specific you need to then understand what the benefits are of each program. All right, but so Dumbox, as I said, great tool for multi-phase flow and elaborated on those transfer processes, flow transport processes, multi-component flow. Yeah. Of course, so those last open source projects were still very much geoscientific. But if you go towards engineering, you will find something which I call the multi-purpose find element solver. So there's a number of commercially derived commercial software which is a lot of physics. So for example, Console Multiphysics or Bacchus are both software packages extremely common in an engineering surrounding. And you know, this is commercial software. It comes with a nice controlled graphical user interface, allows you scripts if you desire, but it's absolutely not necessary. You can control everything over the graphical user interface. You have to pay attention because it's like multi-purpose, so you often buy something like a core program, and then depending on what kind of physics you additionally need, you have to buy extra packages, for example, for groundwater flow or things like this. Again, it's not specifically designed for groundwater flow, but most of those packages or softwares are usable to simulate groundwater flow. And again, it's especially interesting if you want to couple it with multi-physics problems. So for example, if you want to couple groundwater flow with geophysical exploration, so you want to know how, I don't know, the electric resistivity of the subsurface changes based on different groundwater conditions, then you will have a hard time modeling that with VFlow, or I don't think even with OpenGSys, for example, but then COMSOL would be the choice, because it can simulate in one package the groundwater flow and calculate whatever else on electric fields using another package. So there is, you know, a lot of things possible here, and it depending on, for example, the company you're hiring, it might be that they have a COMSOL license because they need it for some other applications, and you can also use it for groundwater flow, right? So it's not specifically designed, so it doesn't has, you know, as I said, some of the user convenience which Spring or VFlow has, as I said, in terms of putting observation points and getting these breakthrough curves for tracer tests and stuff like that. It still, from a physics point of view, is capable of calculating what you need. Yeah, so it's a commercial software and it comes with a price tag. Yeah, and so this is pretty much true for all of those. Depending on if you're in a scientific institution, it might be that your institution has those kind of licenses available. If you get some experience in programming, or at least scripting, such as Python or MATLAB or things like this, you get more opportunities, because there are a bunch of what I call libraries. So a selection of software which require you to program yourself to decide the, you need a combination of the provided functions, but you don't have, program the solution of the finite differences of finite element situation yourself. But still, for your specific problem, you need to choose the right solver. You have to handle pre and post processing yourself. So it's a bit more work, and it requires you to have more pre-knowledge than the other ones which are operating on the graphical user interface. I'm just listing a couple ones here, like OpenFlow, also from engineering, and an extremely popular software library for flow problems. PETSI is more in general an high performance software, or library, pardon, on which a lot of the other libraries will build on. pFlowtron is specifically geoscientific design library for flow problems. Also, I believe, under active development and with huge increase in functions over time. But this requires you to have programming language, and if you don't have it, that's big of a hurdle. But if you get it, or if you get it over the time, I really recommend you to take a look at those kind of libraries, because they are also very powerful and allow you a lot of just modeling a lot of situations. So pretty much what I wanted to learn from this lesson is that you have a choice, right? So there is a lot of software available commercially as well as open source. It depends on your resources. It depends on the scenarios you want to model. But there is software, and depending also on your personal interest, you can make a choice on what you think suits you best. Don't get fooled. Of course, every software needs training, right? But if you, with this course, understanding the basic principles of numerical modeling in a groundwater context, this applies to all of those softwares, right? So the Packlet number or the current Ferki-Levy stability criteria, or general the problem of numerical accuracy, the terms of spatial discretization or temporal discretization, the mathematical background, this all stays the same. So what you have to learn is only how to use the software, or the background you already know. And from my personal experience, once you are in a company or once you're in an environment which uses this software on a regular basis, within 2 weeks, you're good to go, learning the principles and all the other stuff. You're learning on the fly when you require it. Also, do not get fooled that many large companies will have their own in-house solutions for the specific problems they deal with. So if you go to mining companies or so, they often have their own core codes to solve the problem, and you have to get trained on those ones. But again, all the basic principles I taught you in this course so far stay the same. All right. So if you have a choice at all, usually if you hire an Indian company, they will have made the choice for you already. But if not, make yourself familiar with the software that is available, what kind of scenarios you want to model, what kind of physics you need to be covered by the program, and then you can make a very, very reasonable choice based on those arguments, as well as the boundary conditions as I recorded, meaning your, for example, financial resources, your requirements on support, and so on. And there's a lot of possibility, and you have a lot of opportunities to get started. Thank you very much.